Okay, so we choose problem number 1. It is the fixed bias configuration. The circuit shown is called a fixed bias circuit because the transistor's base current IB remains constant for a given values of VCC, which is the 16V, and therefore the transistor's operating point must also remain fixed. These two resistor biasing network, which is the 510 kilo ohms and 1.8 kilo ohms, is used to establish the initial operating region of the transistor using a fixed current bias. The figure shows the fixed bias circuit. For DC analysis, we can replace capacitor with an open circuit because the reactance of capacitor for DC is this one. Xc is equal to 1 over 2 pi times C is equal to infinity. So we can also exclude that in our diagram because it is an open circuit as this equation expresses. So if we use the KVL method, which is this one, so I will just put it in here. So in this diagram, so we can formulate an equation, or in the equation for this diagram for this fixed bias configuration. If we can use KVL for the base circuit, first we can have VCC equals IB times RB plus VBE. So this is for the VCC, which therefore IB is equal to VCC minus VBE over RB. So as you can see in here, we can form it because as we use for the Kirchhoff voltage law, as you can see in the 16B in here, is equal to the IB times the RB plus VBE for the voltage of in here for the B and E. So therefore IB is equal to VCC minus VBE over RB. As you can see in here, IB for and if we think about the Ohm's law, which is the I is equal to V over R, but in this case we use Kirchhoff voltage law. So also for the collector circuit, if we use KVL, the VCC is equal to IC RC plus VCE, which is therefore VCE is equal to VCC minus IC RC. So this is for the collector circuit, which is denoted as the expression. Okay, so first we have to determine the IBQ, the ICQ, VCQ, VB, VE, and VC. So first let us solve for the IBQ. So IBQ is equal to VCC minus VBE over RB. So this is the equation we have been gathered with the standard formula. So therefore, what is our VCC? VCC is equal to 16V minus the 0.7 7V over 510 kilo ohms, so which is equal to which is equal to 30 microfarad U 30 UA, so 30 microfarad. So we already have the value for the IBQ. As you can see in here, with the value of VBE, for the VBE is equal to 0.7 for the standard voltage drop. For VBE, that's the standard voltage drop, which is 0.6 to 0.7. Okay, now let's calculate for the ICQ. The formula for ICQ is equal to beta IBQ. Let us notice that this B is dependent, so we can say that beta IBQ, okay, is equal to, what is our beta? Is equal to 120 times what is our IBQ. As we already finished, the value for the IBQ is 30 microfarad, so times 30 UA, so it's equal to 3.6 mega amperes. So we have now the value for the ICQ. Let us move on for the VCEQ. For the VCEQ, the formula for VCEQ is equal to VCC minus ICRC, which is equal to 16 minus, for our ICQ, minus, what is our ICQ? We have 3.6 mega amperes times 1.8 K is equal to 9.52 V. So we already our value for VCEQ, and for VB, let's say VB is equal to, because you can say that VB minus VE or VBE is equal to VB. Therefore, that expression VB is equal to 0.7 for the voltage drop of our base circuit. Okay, for VE, as you can see, VE, our VE in here is, of course, 0V, because the voltage down, since the voltage in here for E is 0, no voltage flows in it. Okay, and for lastly for VC is equal, also equal for VCEQ, which is also for 9.52 V. We can say that this is VC is equal to VCEQ, because if you get a tester and you test a tester from this VC, and for this, from there and there, you can get the 9.52. And for, if you get for the other one, for the other voltage drop, and for the VC, it is also equals, because since our voltage drop is always 0, so that's why the VC is equal to VC EQ. So that's all.